Cool. Thanks, Vinay. Okay, welcome everyone for our webinar on RocketML Deep Neural Network Software Accelerators. I'm Santi Adwani, one of the founders and CTO of RocketML. The outline of today's webinar is as follows. I'll kick off the webinar with a motivation on why we did what we did in terms of these software accelerators and what they mean. And I'll hand it over to Sergio, who's our chief software architect, and he'll do a deep dive on the tool that we're talking about. And we'll do a quick recap, and after that, we'll take Q&A. So while the presentation is going on, if you have any questions, please feel free to leave them on the chat box, and we'll try to cover as much as possible in the Q&A. So prerequisites for this webinar are very simple. We're expecting some basic machine learning and deep learning understanding from the audience. A little bit of navigating GitHub so that you can get access to the software that we're talking about. Optionally, if you know Docker or Singularity, it's good. Otherwise, there are instructions that you can get started with. So that's as simple as that. So with RocketML Deep Neural Network Software Accelerators, we are trying to address large-scale deep learning for science and engineering problems. So in specific, the examples that I have here on the slide are subsurface characterization, an example from topology optimization, and neural PDE solvers. Like, these are a few examples in the science engineering area. And problems in science and engineering are kind of have a different characteristics in terms of their data and complexity compared to, say, problems in general purpose world. And some of the key differences are in the area of science and engineering, data collection is expensive. So you need a fairly expensive instrumentation like microscopes or satellite imaging or seismic imaging. Or in the case of PDEs, ability to collect a lot of data by doing simulations. In general, the collection is expensive, right? You can't take your iPhone or something and take pictures and make use of it. The second characteristic is data labeling requires expertise, right? So that is, if somebody wants to characterize a scanning electron microscopy image from a cell, it requires expertise in that domain to label the data, and that makes this problem, these problems even more harder. And the data is typically large. That is, you're dealing with, say, 1,000 plus or 10,000 pixel by pixel data, or 3D data, or sometimes even 4D data, because you're dealing with space and time dependencies. So the data is going to be very large in these problems. And the resolution of the data is also fairly important, because you cannot leave away any pixel information or voxel information because you've invested in collecting the data. So with all these characteristics, when you're trying to build deep learning models in these areas, the memory requirements and the complexity in terms of turnaround time can be fairly large, right? So what I'm showing here is a 3D UNet where you have an input-output pairs, and on the right-hand side, I'm just showing you how the memory requirements for training these networks would exponentially grow, as well as the training times will exponentially grow as you increase the problem size. So when you're dealing with deep learning in these areas, the single GPU may not be sufficient. So you need to have a cluster of GPUs, or sometimes even a single node with multiple GPUs to deal with these deep learning problems in these areas. So, but the complexity now kind of increases on domains. Right? So for example, if you're coming from a domain with deep expertise in an area, you need to learn PyTorch or TensorFlow, and they have pretty steep learning curves. Even if you start with them, working with distributed aspects of these things can also be pretty steep. But once you cross that, there is going to be distributed computing complexity. Like, how do you deal with memory management between GPU and CPU, and how do you deal with data movement between nodes, and how do you deal with I/O between parallel file systems, and so on and so forth. The complexity will increase. And in addition to that, you have distributed algorithm complexity, right? So for example, when you have more GPUs, you may want to use larger batches. And when you're dealing with larger batches, you may run into convergence issues coming from your optimization algorithms. So there is a kind of multitude of these problems that you will run into when you're trying to deal with large scale problems. So that's the problem. That's what we are trying to address with these software accelerators. The idea is it's a software that works on a cluster out of the box. That is, whether you're using a single GPU, multiple GPUs on a single node, or a large number of GPUs, whatever your hardware infrastructure is, the software just has to work out of the box without any fine tuning. The second thing is strong scaling. The solution has to scale with your infrastructure and for kind of any data size. So we're talking about upper limits of Amdahl's law in terms of scaling. Last but not least, the time to solution is a key focus, right? So for example, it's not about just having more flops. It's about time to solution. That is, you want to make sure your solution converges to a minima. You want to make sure as you increase your batch sizes, you're not diverging from your local minima and your solution. So that's the motivation behind software accelerators and what these are. So something that works out of the box, strong scaling, and time to solution. So with that preface, I would like to hand over to my colleague, Sergio, who's on the line, and he'll take it away from here and give you a deep dive into RocketML deep learning software accelerator. Thanks. Sergio, please take it.
Yeah, thanks, Santi. Hi, everyone. My name is Sergio. I'm the software architect here at So my goal here today is to talk about the tool specifically, right? So Santi gave a good introduction to our goal as a general goal, and I'm going to focus on what this tool is about and what it's for and what it's capable for, and hopefully answer all of your questions or many questions. So this is the outline for the talk. I'm going to introduce the tool, what it is, the design principles behind it, and who it is for, and also importantly, who it is not for, right? And then specifics, how do you go about configuring it, show some features that I believe make it powerful and so on. And finally, how do you get your hands on it, right? How to install and download and start using it, and where to go from here, what could be the next steps. So what is RMLDNN? Is RocketML's, our company's deep neural network tool, right? So this is a new tool that we believe can allow you to efficiently build and train deep learning models. And in the next couple of slides, I'm going to explain why these, show examples for why it's based on these two design principles, or try to prove why it's based on these two design principles: ease of use and uncompromising performance, right? So why is it easy to use? Because this is not a new deep learning library or package like the ones we're used to using, like PyTorch, TensorFlow, or Keras. No, this is a command line tool that is code-free. It's command line based, not GUI based, but command line based code-free tool that is configuration based. So in a nutshell, and I'm going to explore this much more in the next slides, but in a nutshell, you're capable of just creating some configuration, some map of the run, like this one, a human readable JSON format configuration file, where you specify every aspect of the run, how you want, what, if you're familiar with deep learning, a deep learning run has many aspects about it or modules about it. What's my neural network? What's the data? Where's the data? And what do I want to do with the data? It's pre-processing and post-processing and so on. And all this is specified in a JSON file, just like this one. And you pass this on to the tool in a simple single command like this. And that's it. That's all you need to do, right? So there's no real code to write, new package or library or API to learn. It is as simple as this. And of course, this command, if you run on multiple GPUs or in a cluster, it can gain some attributes like configuration parameters or cluster managing attributes and so on. But the core, the the application itself, all it takes is a single JSON file. And I'm going to explain this also towards the end. Before we dive into the more details about this configuration and the run itself, let me talk about point number 2. Why is it uncompromisingly fast, right? So RMLDNN is from the get-go written with distribution and parallelization in mind, right? As opposed to most of the popular libraries and packages out there for which parallelization is an add-on, is an after-the-fact thought, right, or addition. RMLDNN has it as its basic premise, and it was based upon this. So it uses these low-level libraries for distribution and communication and so on. And in doing so, the interface for you to use it on a single machine or in a cluster with hundreds of GPUs remains the same. So the thing I just said before, configuration files, simple command line, remains the same. It behaves the same way, either on one GPU, and it just gets faster as you go to a cluster, say, but the interface is the same. And it'll abstract away the complexities of distributed computing from you. So things like partitioning the data or communicating between nodes, reducing gradients, if you know what that is, all this is abstracted away. You don't have to do it, right? And with that, we claim we achieve HPC grade scalability, right, on both CPU or GPU clusters. And these plots here are just 2 examples. We have many use cases like those, but 2 examples showing the scalability that I'm talking about. So on the left-hand side, I have a speed up curve, right, for a run performed on a cluster of CPUs, and on the right-hand side, GPUs. And I'm showing epoch time as a function of the number of processes, be it CPU or GPU processes. And the green line is the speed up curve, right? How much time you save by, say, in this case, doubling the number of processes. So ideally, as most of you know, you'd expect you want a straight line. You don't expect it, but you want a straight line. That's the ideal case, right? So as the closer you get to a straight line, the better speed up you get. And we get very close, right? In both cases. Even here on the right-hand side, we go up to 512 GPUs. That's 64 servers of 8 GPUs each. And we get pretty good, very good, almost linear speed up all the way up there. Right, so these are the basic 2 design principles that I mentioned. So moving on, who is this tool for and who it isn't for, right? So I'd say it is for a big range of people, right, with a vast span of experiences and use cases. I'd say it covers all the way from a newcomer, a guy who, knows a little bit about machine learning, but wants to get into deep learning, and maybe doesn't want to spend all the time learning Python or PyTorch or Keras, any of that, right? Maybe I don't know Python and I don't want to learn right now, not for this. All the way to someone who is pretty experienced, has been writing PyTorch code or Keras code, but maybe lacks the knowledge or the time to worry about distribution. I don't know how to scale it up to hundreds of GPUs and make it performant at this level. So, and anything in between, right? So these 2 extremes could benefit and will benefit from our tool, and many things in between. Maybe some data scientists with scikit-learn experience, right, that want to learn and start to use deep learning. That's also a good use case. So I'd say a vast range of experiences. Who it is not for, it's people with a lot of experience, right? So maybe very experienced researchers or data scientists writing advanced deep learning code. So for example, if you're using PyTorch or TensorFlow in Python, and you need maximum flexibility to write your own custom layers and optimizers and loss functions and whatnot, this tool gives you it gives you a lot in terms of ease of use, low barrier to entry, and performance, and maybe the price you pay a little bit is flexibility. So you can't do anything you want like you could in Python, right, which is a full-fledged language. With that said, of course, the goal is to grow and expand the tool as fast as possible. So if you think of a use case, if you have a use case that might not immediately be fulfilled, of course, talk to us, and we can always expand the tool and add features and add coverage. But that's the main idea. All right, so moving on. Yes. Now for the second part of the talk, right? More specifics about the tool and how to use it. If you have any experience with deep learning, you know that to configure or to write, say, a deep learning script using any package you might want, you have to worry about these modules, these parts of the run that are important, right? So you need to define and write and maybe use some data loader to load the data in, and maybe some data preprocessor to do data augmentation or manipulation of some kind, some filtering and whatnot. And then you write your neural network in PyTorch or Keras. This is done via APIs, right? You have an API to create a layer, to connect the layers and so on. And you have to pick an optimizer. You have to define a loss function and use a loss function, and maybe do some data post-processing, do something with the result, right? So these are the basic building blocks of a deep learning run. And like I flashed before, this configuration file of RMLDNN has that kind of granularity and modularity, right? I would say. So each one of those modules is represented here through some piece of JSON block where you in human readable fashion, you specify what it does. And let me give you a few examples and dig a little deeper into each one of these. So for the layers, this parameter layers specifies the network. So instead of writing code to create your neural network, you pass a file, a JSON file, which will have the description of the network. So for those who have used Keras, this is exactly what the JSON file that Keras writes out. If you build a model in Keras and write it out, you can export the JSON like this. So it's a simple layer by layer description of the network. Each layer has its own features and parameters and so on. But this is simply a network description. You can easily get it from Keras. Or as we have done, we have prepared lots of these and tested lots of these and put them out in our GitHub page. So, and I'm going to show this later, but you can go there and find lots of pre-built JSON files like those for all kinds of problems, classification, segmentation, object detection, etc., that you can readily use. Or of course you can also, and there's more being added, we're going to keep growing that list. Of course, you're free to take any one of these and modify them, right? So oftentimes you need to customize these networks a little bit. Sometimes you don't, you just use them out of the box as they are. Whatever the case, you could customize them, get these JSON files and change them manually if you want. Or if you really want something more custom, a network that is customized, you can write your own. We've done this many times. You can write a little piece of Keras script or Python script, or use some Keras library like segmentation models and Keras UNet, if you guys have seen those. The Keras UNet is a powerful package on top of Keras that just spits out the network, right? A model that you can train with. So if you import that package, you can say, do something as simple as this. You can say model equals some configuration of the network. And when you call to.json on it, it spits out that JSON file. So that would be for a more custom network need. And let me clarify this. When I said before that if you need a lot of flexibility, right, this tool might not be for you. Well, here you have a lot of flexibility already, right? Just to be clear, with the network architecture, you can create any network you want. Let's say any network that Keras would support. Let's put it this way, right? Any architecture, and be it programmatically by writing your own little script, by using some package to create a JSON file like this one, or using one of ours. But there's a lot of flexibility in the choice and architecture of the network that you can use. What else? In the config file there, you saw a bit of a section here on the JSON about slicers. What this is, it's this nice feature that allows you to slice the input data as a data generation engine. So let's say you have a big blob of NumPy data, right? Some cube of some sort of data, and you want to slice it, maybe tile it, get a bunch of 2D tiles out of it, or a bunch of 3D little bricks out of it, right? Whatever it is, you can do this in memory at runtime using this slicer feature that we have developed, right? So with a little bit of configuration like this, you can say, hey, out of this cube, give me slices, 2D slices of size 128 by 128 with some stride, some overlap, maybe some padding and so on. And the tool will extract those, cut those, chop the block, produce the input data, and use it for training. And so you don't have to do it. You don't have to do it up front. You don't have to write code to do it. It's built in like this. Also, and I'm sure everybody who has done some kind of image-based deep learning classification or segmentation has gone through this. Say if you use Python, there's Torch Vision, sorry, PyTorch. If you use PyTorch, you must have used Torch Vision to do image transformation, right? For augmentation purposes. So you take your images and you rotate, flip, zoom, and whatever. Here, all you do is you pass this bit of configuration in the JSON saying what operations you want done with the images, and it'll do it on the fly as well, kind of like Torch Vision, but without code. And finally, the good old optimizer, say, right? You don't, in PyTorch and Keras, these are mostly done for you. You don't have to write code for those, but you have just to specify. Here, same thing. You just say, hey, I want optimizer add-on with some learning rate, and there's other parameters depending on the optimizer you can specify. By the way, I forgot to say all these features, the whole map of the treasure there for the JSON, this is all documented pretty well. There's documentation in the GitHub page that I'll point you to. So all these parameters, of course, are documented. You don't have to guess anything. But so yes, for the optimizer, we have implemented most of the popular PyTorch optimizers, plus things that are not in PyTorch, like Lars and Lamb are large batch optimizers that are very good for distributed computing, where you want to keep your you want to be able to increase your global batch size without losing performance and generalizability. So these are good optimizers that we have implemented. LBF-Jess is a second order optimizer that you might have heard of, very good in certain situations. Loss function, same thing. You can pass on the name of the loss that you need. We have implemented the typical ones, plus these in bold here are typical losses used for segmentation problems that we have implemented as well. And like I said, this list should and will grow based on need and feedback and so on. Okay, so that's it for parts 2. And just to wrap up part 3, how do we use it, right? So this, like I said, this is not a package. It's not a library. So you don't get to install or build anything, right? It's a command line tool. And you don't want to build this thing either. It's not trivial to build it. You know, even if you had the source, it's a complex tool to build based on the dependencies that it has. But we have made it available as a container, either a Docker container or a Singularity container. Right? So if you're not familiar with these, containers are just ways to emulate a subsystem inside your machine, right? You can have a Linux system inside a Windows machine, or a Linux system inside another Linux system. And within the system, things are already installed for you. So that's in a layman's explanation of what a container is. But anyway, Docker and Singularity are good popular container infrastructures. And for those who don't know, if you do something like this, if you pull a container, like on the left-hand side, if you do a Docker pull RocketML container containing RMLDNN, you have it available for you to run right there on your machine. You don't need to install anything. You just run it inside the container. It behaves pretty much as if you were running natively on the host. And Singularity is a newer container infrastructure that is actually very good and better than Docker, I would say, in some aspects of security and ease of use, I believe. But just to give you, now I'm going to jump out of here and show an example of how you'd go about. Can you guys, Vinay, can you still see my LinkedIn page here? My GitHub page. Sorry.
Yes, I can.
Okay, thanks. So this is our GitHub page, which I'll pass a link to you. And pretty much this is all you'll need. I mean, everything I said in the presentation is pretty much repeated here, the examples, the details, and so on. And in this bottom section here, I show for each scenario, if say for Docker, how to get the image is here, the Docker image, the Docker container. And if it's Singularity, this is how you do it. It's both single command lines. You'd have to install Docker or Singularity, but this is pretty easy too. And there's instructions here. But once you do that and you get the image to run, say using Singularity on a single GPU, this is how you do it right here, right? So the command line that I showed before is here, and the rest is just saying, hey, run Singularity, passing the image name that you just fetched up there, and run the tool, right? And like I said, if it's Docker, there's an explanation here as well. Say multi-GPU Docker, it's right here, right? You put a bunch of parameters. Docker is more verbose. You need to say all these things about the user and so on. But then at the end of the day, you run the tool. And in this case, I'm using 4 GPUs, right? And that's how you do it. So there's detailed explanation here. But the bottom line is it's always this for the command line of the tool, plus some decoration around it to run Docker, to run Singularity, to invoke multiple GPUs and so on. But it's basically the same, in all cases, it's the same idea as before. You build your config file and you run it. There's a healthy and growing section on tutorials here where you can see examples, like step-by-step examples of some tasks being solved. Say, for example, image segmentation. I'm gonna, there's a whole explanation about the thing. Say a config file that you'd use, right, to run RMLDNN for this task. And then here's it, here it is how it runs, or the command line to run it, right, and so on. So please take a look at this GitHub. Oh, I forgot to say the documentation is here. This link. The font here is bad, but it's hopefully it's on this machine. The font is weird. But anyway, documentation of everything I said, how to configure every single parameter there is all in here. And that's pretty much it. To wrap up, so where do you go from here? Like I said, check out the GitHub repo, please. Take a look at the tutorials. If you have questions or feature requests or, well, how do we do this? Or, well, first read the documentation, of course, but please feel free to write to us and submit a tickets and problems or requests or questions. And hopefully, people can contribute with new tutorials, right? You might solve a problem using this in your work or research or whatever. And, it would be nice to hear from you and get new tutorials from people using this. Okay, that's all I had. Vinay, Santi.
Okay, yeah, thanks, Sergio.
Sure.
So we have time for a lot of time for Q&A. And before that, I just want to quickly recap and motivate the conversation for Q&A. Let me share my screen. So just to recap what you heard from Santi and Sergio, RocketML Deep Neural Network Software Accelerator is a tool for efficiently building and training deep learning models. And it's built on 2 main design principles, as Sergio mentioned. First one is, of course, ease of use. You don't have to know any Python language. And also, you don't have to know all these large frameworks. Sure, if you know them, if you want to use them, you can use that. But when you want to train a model with minimum amount of time wastage in figuring out how to distribute, how to make it work with GPU, CPU, all those stuff, you just feed a configuration file with specific configuration instructions and run a command line, and you can solve a large number of problems. And we'll continue to grow support for new types of problems that we can that you'll be able to solve. And the tool itself will remain free for use for all of you. And it is, as Santi shared earlier, the motivation for this tool came from solving science and engineering applications, but it doesn't mean that you can't use it for general purpose applications of machine learning, but its sweet spot, we believe, is in the science and engineering side. Please join us on a LinkedIn group. We have formed a LinkedIn group called SciML Group, Industrial Grade SciML Group. We can change the name of a little bit. I'm thinking of different, I'm getting some advice on that from other participants. LinkedIn groups are great to collaborate, and one way for you to also become a leader in this area and share your content and build the community, right? And I'd like you to join the LinkedIn group. The link is here. And then obviously, as Sergio mentioned, everything is on GitHub. Download, copy, clone the GitHub, or do whatever you like to do typically on the GitHub. And also, I'd like you to contribute to our repository. The two ways you can contribute are submit issues. If you want a new use case supported, feel free to add it there. And the more people request that, and we'll be motivated to also hustle and get it done. And then second thing you can do is write tutorial. You will become a contributor, particularly if you're a student or want to build your career in the machine learning, deep learning space, solving science and engineering problem. It's a great way to get started and write the resources, write the tutorials, and ping me or Santi or Sergio, and we can help you how to do that. We'll give you some templates that makes the work a little less complicated. And that's kind of the recap. And I want to run, as Santi said, please post if you missed any topics here on the chat window. I probably should have given a choice for you to write it right here, and I'll share. It looks like there's a lot of interest on scientific machine learning. PDE solvers are pretty much under that umbrella, and that's good. And that's really the red hot topic at this time.
So I have two comments here, geophysical inversion and segmentation. So geophysical inversion here, you mean sign of segmentation problems, or talking about FWI or something a little more complicated here, Adebayo?
Yeah, feel free to unmute yourself
and
ask questions. This is Q&A time. We have 15 more minutes. We can spend on topics of your interest too.
Yeah, thank you for the presentation. Geophysical inversion, I mean, if I have some forward models for some geophysical method, and I'm trying to use machine learning and deep learning method to find the distribution of parameters in the subsurface, maybe in 3D, in 2D, in 1D. Yeah, that kind of work.
So you already have some simulation data from running a simulator. You have the input output pairs for this. Is that a fair assumption?
Yeah, probably that kind of data, synthetic data.
Right.
Synthetic data, okay.
Synthetic data, perfect. Okay, awesome. And DICOM image segmentation. So here, Manjunath, you're describing a problem where you have a whole bunch of DICOM images, 2D or 3D, and you're doing multi-class segmentation. Is that the problem?
I was trying to do 3D segmentation of cerebral vessels, blood vessels. So in most of the cases, I have CT angio or MRI files. But in that case, we can only get the flow component, but not the vessels. Is there something that can enhance, get the vessels, or that slide? There will be only a slight variation in the contrast between the surroundings and the vessel.
Okay. Okay. I see. So if you could just post some kind of data set or pointer for us on GitHub, right? We definitely take a look and we can follow up on this thread, Manjunath. That'll help.
Yeah, we'll try to do, because mostly I work on patient-specific cases. So I don't know, I have to get some consent on anonymize the data. Only after that I can share.
Sure. I mean, not necessarily the data, but just some pointers on paper or an example case would be fine. Okay, cool. Thanks.
Yeah, we'll try to do. Thank you.
As the question, is the tool available for commercial use cases? Yes, it is. We have a enterprise approach to engaging on those types of things. Feel free to ping me. I'll help understand how. We have another whole platform approach where a lot of the data science functionality is also covered, in addition to security. The typical enterprise companies care a lot about security of the data, and they have the proprietary data, proprietary IP. They want to build proprietary models. So we kind of focus on that aspect also. So this can be used for commercial use cases also. I should, thanks Karthik, great job. I should add one more point here. If any of you want to present in the next webinar series that we'll be doing, definitely would like to highlight your project. I think all of you are one way or the other working on very interesting use cases. Most deep learning use cases are super interesting anyway. And we can definitely promote your webinar and your topic and have a good discussion, and potentially someone else can jump in and help you out too from this crowd, right? So feel free to ping me either on LinkedIn or on the GitHub issues. You can comment on the GitHub issues. The best way is really to kind of join the LinkedIn group I mentioned earlier. And let me get the link and post it here so that at least some of you who are still hanging around can join right away. Oops.
And we have a few questions also. We can.
Yeah, why don't you address one while I figure out how to post this?
So thanks, Karthik. So the question is, how does the performance compare with Kuden on some of the presented examples? Sergio, you want to take that?
Yes, yeah, thanks. So we don't have direct comparison with Kuden. We use Kuden behind the scenes, in fact, right? So it is one of the libraries that we tap into for our tool. It uses Kuden. So I can't really compare directly to it. It's like we're using it already. What we do have is comparison against, and I haven't shown it today, but I can share it with you. Comparison against Horovod, for instance, right? We have used Horovod in our tool to solve the same problem and have seen better performance using RMLDNN. So, but not directly with raw Kuden because we use it behind the scenes.
Yeah. So just to add on this, so Kuden is part of the stack, Karthik. It's not an alternative to Kuden. It's basically an alternative solution compared to, say, PyTorch, TensorFlow, or any other distributed deep learning tool out there. Right? So it's a different layer at which we are trying to address.
Fantastic. Thank you, Sergio. Shanti, very good to meet you after a long time.
Yes, same here.
And Vinay, thanks again.
Thanks, Karthik. Yeah.
The next question is, if you had to choose to focus on one of your two key principles, which one is your bigger focus between, guessing, ease of use and uncompromising?
That's a hard one. We like both.
Well, it's two sides of the same coin, I think. You know, if the tool has great scalability and stuff like that, but is hard to use, it becomes very exclusive to few people who know how to mess with it.
Yeah, I guess I chose the word uncompromising performance, right? So I guess that kind of skews the balance towards performance, meaning whatever we do, we cannot compromise performance, right? That there's no compromise with performance. So I'd say that kind of implies that we favor performance over everything else, but we have tried and succeeded so far to keep the interface as simple as we want as well. So ease of use has continued to be a priority.
Yeah.
So yeah, I'd say both, but if we had to kill one, no, I'm kidding. They're both very
No, I think you're right. Just to build on what Sergio was saying, we've learned the lesson that ease of use is equally important, and it used to be performance always was used to take the higher preference for us because that's what we focused on, and it delivers a tangible benefit to our customers. However, ease of use democratizes the tool, and it brings in a lot of the domain scientists who want to do deep learning, but they don't have time to learn all these massive, frameworks that keep getting larger and larger and larger. And so the ease of use in the science and engineering has become very critical. It's reaching a point of criticality of performance too. So I would say it's two sides of the same coin for us as far as we are concerned.
Cool. So there's another question from Tanya. If I understood correctly, the tutorial on Poisson's equation using the simulated data upfront to compute the solution in the whole domain. However, is it possible to change the loss function and use physics-based loss function without data? So Tanya, let me share my screen and just kind of walk you through this. So within the framework, you could basically solve using two approaches. One is you can simulate your data input-output pairs and train a network. So that would kind of become any other image segmentation or kind of an image-related problem. The tutorial we have here actually is using a PDE solver without doing any simulated data. So if you go through this, the idea here is we are creating a loss function based on the physics. And that's the loss function that you assign for training the network. So let me show the section here. So within the tutorials, right, and within the documentation, we have this entire section on loss functions. And here, the loss function that you assign is a loss function for Poisson 3D, right? So what that means is we are not generating any simulation data ahead of time. We are actually using physics-based loss function. The data that we are generating and using is only for the input data pairs, right? For example, we are generating a whole bunch of diffusivity properties as the input data for training, and then using a physics-based loss function to train the network. Okay, so if you want to train your own neural PDE solver for Poisson problem, all you have to do is bring your own material properties, keep the same Poisson loss function as long as it's the same boundary conditions, etc., and retrain it. And that should basically address your problem. Any other follow-up questions on that? So this maybe we'll do one complete webinar on just neural PDE solver for Poisson. That way, I think some of the distinctions between data-driven methods and data-free methods, that distinction can also be clear.
Thank you so much. Actually, I'm curious to know where should I need to define the PD? In which file?
So right now, great question. So right now we have defined a few PDE loss functions. Okay, so let me go through this. So it's probably a good time to show the documentation. Okay, so within documentation, we have a few section for loss. And within the losses, these are the PDs that we support today, right? So the data-free neural PD solvers support is limited to these three equations: Burgers, Poisson 2D, and Poisson 3D. Okay. So if you have your own PD loss service, own PD, let us know, right? Because there are two things that you need to understand for data-free methods. One is defining the loss function for each of these PDs will be different, right? So for example, you're going from 2D to 3D, from Poisson to say nonlinear elliptic equation, the loss functions have to be defined accurately for the network to converge. So we basically have a suite of PDs that we have already worked on and made sure they work, and we add more of it, right? So what that means is we'll add more PDs here. But if there is a specific PD that you're interested in with some variations, let us know so that we can add that PD into our suite.
Oh, okay.
Okay.
Thank you so much.
Yeah. So let us know what PD, and we'll work with you on that. Okay.
Yeah, that's where you would enter an issue in the GitHub or reach out to us directly also. Let me put my email address also.
Yeah. If I were to implement, for say, all our PD similar to Burgers, how do I go about it? Same here, right? So let us know and we'll add. And keep an eye on the loss functions here, because this is an area that will grow, mainly because when it comes to data-free PDs, solving PDs using data-free methods, the loss function definitions and how to navigate between convergence and accuracy can be fairly tricky. Okay, so that's why it requires a little more experimentation before we productize it and put it here. So just ping us on GitHub or send us a note here, and we'll work with you on getting the PD. Hope that answered, Marty, for you too. Excellent, thanks. And if you are okay generating the data, right? For example, you're not so much into data free, but you want to build a neural PD solver or a surrogate model using your own data, then the tool can be used right out of the box. That is, you have this input-output data pairs, and you have a whole bunch of loss functions, and you can train your own PD solver using the tool out of the box, right? So that's an alternate approach that you can do while the data-free approach is being figured out. Yes, so there is a notebook for Poisson's equation. So if you go to the tutorials and neural PD solvers, that's a Poisson solver. So here, this is the notebook where the notebook kind of describes different steps. You might want to kind of go through that. This can be executed as it is, as long as you have Singularity installed or Docker installed. This one is built for 3D problem. I think something similar should work for 2D also. But yeah, try this out. Buckley Leverett would be interesting. Okay, cool. Thanks, Karthik. I'll look into that. Taking a note of that.
Tricky, but interesting.
Okay. Okay.
All right, let's wrap it up.
Yep.
Okay, there are more questions.
PDs with Dirac delta. So this is coming. So we are working, I mean, having non-zero right-hand sides, right? That is so that you can solve your own functions is basically on our roadmap. So these are all. Yep. So keep an eye on the LinkedIn group or on our LinkedIn so that we can let you guys know once these are ready to.
Yeah, and ask questions on GitHub also. Like as I said, just ask for things like I want support for this and that, and we'll keep working on it. And the idea is really to solve the scientific problems. Right? That's the that's the goal here, and not mess with the tools. Most scientists don't want to do that. Right? Even though they are quite capable of building their own tools, they're very talented and capable, but when you can solve a bigger problem, let's focus on that. With that, I think we are at the end of the hour here, and we'll wrap it up. Thank you for attending the webinar. We'll try to do this at least once a month, and if there is more interest, probably more often. But we'll pick topics of interest for all of you. And this is, again, community building is part of the equation here. The more people are interested in these types of topics and the more they engage, the more we can increase the awareness of this topic. And we'll also create a Slack group. We actually have a Slack group for scientific machine learning. And I'll send the invite to some of you on the LinkedIn. I don't think I have your email addresses, but I'll send an invite on the LinkedIn. And if you can join the Slack group there also, we can communicate and message each other. All right. With that, thank you very much for attending the webinar. This is our introductory webinar, and hopefully you learned a bit, and thanks for the contribution and engagement, and talk to you next time.
Thanks, everyone.
Thanks, everyone.